Okay, let's get started. Our agenda for today is a quick introduction of who we are and what our products do. We'll go over the pipe filling and draining feature and Impulse. We'll do a pipeline draining demonstration and a fire system filling demonstration and some key takeaways and resources. A little bit about who we are. DataCore has been around for 43 years. We have many software products, including engineering simulation. These products are sold in over 100 countries with dozens of distributors around the globe, and our engineering simulation products are used in over 400 universities. These are some of the industries that you can find our products in. The big ones for this probably include power generation, municipal water, pipelines, and manufacturing. This is an overview of our pipe flow modeling products. They basically break down by incompressible and compressible and steady state or fast transient. We also have some modules in addition to the base products, including extended time simulation, goal seek and control, our slurry module, and pulsation frequency analysis. Today's focus is on Impulse. Going over some general Impulse capabilities. If you're not familiar with Impulse, it's meant to model rapid transients, particularly for water hammer or surge analysis. We can model realistic pump behavior, including 4-quadrant curves, positive displacement pumps, and other types of pumps. It's often used for sizing surge mitigation equipment. This can include accumulators, tanks, air valves, things like that. And we're also able to do frequency analysis in the force and pressure domain using the PFA module. So for an overview of the pipe filling and draining feature, software used to model water hammer and other rapid transients and fluids usually assumed that all pipe stations are liquid. It may assume that all of the mass entering or exiting the system is liquid. Any gases and vapors will exist at fixed locations. This is very common in cavitation modeling methods. Gas thermodynamics are simplified with fixed assumptions. They may be forced to be adiabatic, etc., or even treated as incompressible. And gases may only exist in certain pipes or do not travel from pipe to pipe. And the net result is that the impact of gas pockets on water hammer and pipe forces is not adequately captured. The pipe filling and draining feature addresses these limitations. It allows you to track gas pockets as they move throughout the system, they expand or contract, and as they enter and exit the system. The gases can be air or something custom. The gas thermodynamics are customizable. You can specify molecular weight. Expansion and compression can be isentropic, but it can also be isothermal, or you can use a custom polytropic process. So when would you want to use this capability? Well, for draining applications, it could be pipeline draining as a result of a pump trip or routine system shutdown. Maybe you want to model purging a line with an inert gas like nitrogen, or modeling leaks or more catastrophic system failure or a control valve failing open. For filling, you can use this to model plant startup or perhaps modeling systems that start dry, such as fire sprinkler systems. But there are a lot of other uses for this feature. Maybe your process fluid is the vapor and you want to model water hammer occurring from some fluid entering your pipes. Maybe air entering and exiting a system from a vacuum breaker valve as a result of water hammer. Or some part of your system uses gas for surge mitigation. We do have a gas accumulator at junction, but this is another option that may have advantages for certain models if you want to model it with friction and the height effect. The interface doesn't necessarily need to be a direct physical contact. It could be used to model a piston between pneumatic and hydraulic components if you want to treat the piston as frictionless. So feel free to get creative with it once you have a good grasp on the modeling assumptions. And if you're not sure whether this modeling approach is a good fit for your system or for your product, you can always reach out to one of our sales engineers. It's also possible that one of our cavitation models or partially filled pipe options will make more sense for certain analyses. So we're here to help if you're not sure what approach you should take. You can visualize gas pocket volume and interface location in a number of ways. Naturally, this includes numeric output, but it also includes animation layers as shown on the right, or transient pipe graphs and profile graphs. Uh, Either of these can be animated. You can also perform force analyses, and this gives you the ability to export your results to pipe stress analysis software, such as Caesar 2. And pipe filling and draining works with our other features, such as Scenario Manager and multi-scenario graphs, which help to analyze how the presence of gas pockets impacts the transient pressure surge and flow within a system. So some of the theories and assumptions you should be aware of. The liquid component is still modeled with method of characteristics. Boundaries move at the same speed as the fluid that they're connected to. The gas volume is just treated as a bulk compressible volume. The friction for the gas volume is ignored except at the system boundaries. Otherwise, it's assumed to be dominated by the liquid component and therefore neglected. There is no stratification or mixing, so you can't have a bubbly flow when an air valve opens. It's also perpendicular for the gas liquid boundary to the pipe. The gas pressure losses are modeled, but only at the gas vent boundaries, not at interior junctions. So most of the junctions are essentially ignored when they're in a gas bubble. It's also worth noting that it's not compatible with certain features, such as the infinite pipe option, the unsteady Brunón friction model, variable fluid properties, or the pulsation frequency analysis model. It's only appropriate when the interface movement is slow relative to the speed of sound. Gas and liquid flows cannot mix at branches. It either has to be fully gas or fully liquid at each station. And each bubble has to enclose at least one of the stations used for method of characteristics. So the sectioning is going to matter a lot. I would recommend at least 10 sections per pipe, at least for the pipes that the bubble is passing through. There may be dead branches in your system that aren't affected by the bubble that are just used for pressure probes or things like that. So you don't have to have fine modeling in all of those, but at least with the bubbles passing through it, you should. And potentially more for air valves if the valve is chattering, because as it's opening and closing, you could have smaller bubbles than if you just have, exit valve that's always open or something like that. So keep that in mind if you're modeling a system with air valves or vacuum breaker valves. So to enable pipe filling and draining, it's located in the transient cavitation panel within the analysis setup window. And this is mutually exclusive with the cavitation modeling options, which are DVCM and DGCM. You have your gas bubble settings here as well. And these apply to all bubbles within the system, but there are other things that you can customize per bubble, which we'll get to. But the gas type by default is air, or it can be user defined. So the molecular weight and gamma are already pre-specified if you choose air. The compression or expansion thermodynamics are adjustable. So you can do it isentropic, which will force n to be equal to whatever gamma value you put in or the default value. You pick air, or it can be isothermal, treating n equals 1 for the polytropic polynomial, or it can be polytropic with a specified polytropic index. Often you'll want to choose something between 1 and gamma. So this would represent having some heat transfer with the surrounding pipes and liquid, but not rapid enough heat transfer for you to approximate it as isothermal. And this also has these expandable artificial transient resolution settings. And these compare pressures at each station between different blocks to check if they're within a specified tolerance. The block size and number of blocks that must pass the test in a row are adjustable. You can also adjust the tolerance parameters. There's an option to bypass the artificial transient resolution stage, but you should only use this for troubleshooting. So a little more information to understand what artificial transient resolution does. We have to understand a bit more about how the gas pockets are initialized. So the first solver stage is purely steady. This is basically the same as Fathom, and it's entirely liquid full. So the second stage is where that artificial transient resolution happens, and this is a pseudo steady state. So the liquid is modeled with the method of characteristics, but there are voids in the liquid where the gas bubbles are located. Essentially, the liquid is moving and the bubbles are stationary. And once the liquid region solution is stable, the true transient phase can begin. And then the third stage is what you're familiar with from impulse normally. This is fully transient. So once it hits this stage, the fluid volume in tanks and accumulators can change, and the transient events you specify for your junctions can start to occur. The gas-liquid interfaces can move in this stage, and gas pockets can now expand and compress. And more massive gas can enter and exit the system. But one thing to note about the artificial transient settings is that the sectioning can actually have a greater impact than artificial transient resolution settings on the artificial transient. So make sure that you're checking your sectioning as well if you're seeing artificial transients. But it can help to tighten up these tolerances. So these are the 6 junctions which can be used as gas vent boundaries. You can do it with air valves, assigned pressure junctions, spray discharge junctions, exit orifices, exit valves, and relief valves. And the gas through the venting boundaries behaves isentropically and can supply or discharge to the system depending on the pressure difference. Flow entering the system through air valves is always a gas. Otherwise, for the other junctions, it depends on whether there's a gas or liquid at the pipe node connected to the junction. And because of that dependency, systems without air valves must be initialized with some gas in the system, or they would remain liquid full throughout the simulation. And except for air valves, the junction must be specified as a gas vent. And this is an optional tab of the junction property window for each junction, as shown on the right. The gas CDA and external gas temperature can be specified here. And if it's not specified as a gas vent, gas will not pass through the junction, and it will trap a gas bubble when that bubble reaches the junction. At which point fluid upstream of the bubble will not flow through the bubble. It will only compress it. So if you notice that the flow is coming to a stop on some line, this is something to check. But in terms of loss modeling, the liquids will always use the loss model that you specify in the normal loss model tab, which you can see on the left, as you do in other analyses for impulse. But the gases use a discharge coefficient loss model with the gas CDA specified in gas vent properties. And if you're using a discharge coefficient for the liquid loss, it doesn't have to be the same CDA. And the gas flow can be sonic or subsonic, and sonic choking is modeled, which limits flow and through the boundaries. So once you activate pipe filling and draining in the analysis setup window, there will be this new filling and draining tab in the pipe properties window. And these pipes can either be liquid full, gas full, or have an interface within the pipe. By default, they'll all start as liquid full. But if you're modeling pipe filling and have a lot of pipes that therefore start as gas full, the global pipe editing tool is useful to configure the gas region of the model quickly. You should pay attention to the direction of the interface because it does matter, and you can flip it if necessary. So you can see here that the upstream and downstream junction are displayed to help with this. And the initial interface position may be adjusted within the pipe. You can see there where it says liquid percentage 50%, which is putting it halfway through that pipe. If you do need more than one interfaces within a pipe, what you can do is break it up into multiple pipes in the model, even if it's one physical pipe, and just have them connected by lossless branches. Not all interfaces must be within a pipe. The interface may also be located at a closed valve between a fully liquid and fully gas pipe. And for gas pockets spanning multiple pipes, you should check that the bubble uses the same temperature and pressure across these pipes. You'll get an error. And the initial pressure and temperature are adjustable. So you can see for the pressure that you can use the ambient pressure, or you can specify the pressure for the bubble. And for the temperature, you can use the liquid temperature or a user specified temperature. So often, if this is a bubble that's starting at a system boundary, you would use the same temperature at the gas vent and for the bubble in the pipe. So the first example is for system draining in a pipeline. So this is meant to model your typical pipeline situation, especially for downhill pipes, where you can place a vacuum breaker at a high point to let air in to avoid the pipeline crushing from the pressure difference. These sort of siphon events can happen from an upstream pump trip or a valve closure, or maybe there's an equipment failure downstream, such as a leak or a control valve failure. But if the pressure in the pipe is too low, the pressure difference with the atmosphere will actually crush the pipe. So for this example, we're modeling the latter, where it's failing downstream, maybe a control valve failing or a leak. So let's go over to impulse. So first we'll go over to analysis setup. And we'll set the fluid impulse standard and double click on water. We'll just set this to 70 degrees. And let's go down here to the transient cavitation panel. Let's switch that to enable filling and draining. For this example, we'll just leave it as isentropic with air. And this is where we would change those artificial transient resolution settings. We're not going to touch these in this case, but we will adjust the sectioning. Go ahead and hit OK. Now start with dragging an air valve. For the sake of simplicity, we're only modeling the downhill side of this system where it's failing, but you can model both sides. And have a branch and then assigned pressure. We'll double click on the pipes tool to connect these with pipes. Okay. Now these pipes, we can go ahead and set them up individually. We will use ANSI steel. So set this to steel ANSI, and we will do 6 inches. We'll leave the friction model and the wave speed as default. We'll set the length on this to 100 feet. It remembers the size when you go to the next pipe, and you can just set the length here. You can also copy this from pipe 1 if you have pipes that are identical. Set that to 100 feet. Okay, so those are defined. Let's set up the elevations on these. We want the air valve at 100 feet. We want the branch at 50 feet. I'll have the assigned pressure at 0 feet. Now for defining the other air valve properties, we'll set it to vacuum breaker and gas release. We're using gas external pressure of 0, gas external temperature of 70. We can leave those. That's just measuring the fluid temperature. Then this is 0 PSI gauge. Um, we'll change these to square inches. Let's start with 1 square inch for each and change the number of connecting pipes down here to 1 pipe. And in this case, we don't have to set it as a gas vent in the optional, since all air valves are assumed to be gas vent boundaries. So here, just hit OK. The only thing that we were defining in the branch is the elevation, so that's fully defined. So for the assigned pressure, let's use PSI gauge and set this to 45 initially. We'll leave that as stagnation. And go into optional, here's that gas vent properties option. So for the gas CDA, we'll make this one large so it doesn't affect the behavior much when it hits it. So this would be more of a leak sort of scenario, or a catastrophic failure. But this is our worst case scenario we're modeling. And again, let's just set this to 70 degrees. And then we can set up a transient here. So the first value is filled in automatically. And we'll just have it drop to atmospheric pressure at 2 seconds. So 0 PSI gauge. And we'll do a 10-second simulation duration. So at 10 seconds, still be at 0. And that should be fully defined. Now you can go over to this tools menu and hit the design alert manager. Click the plus to make a new design alert. We can call this one minimum pressure. It applies to pipes. We'll change the parameter to static pressure. And we want it to be less than or equal to minus 10 PSI gauge. We'll apply that to pipe 1 and pipe 2. Once you've done all that, hit OK. Now we can go set up that sectioning. So sectioning is normally done automatically. However, in this case, we want it to be finer. So instead of leaving it on automatic, we'll change it to fixed count. And since we're modeling a simpler system and we want at least 10, let's go ahead and set this to 20. Then the simulation mode and duration can be set to 10 seconds. Okay, so here it's saying that the assigned pressure is undefined. It says the gas vent CDA must be less than the flow area of the connected pipes. So it looks like I left this on square feet instead of square inches. So if you see that, just change that there. Now all junctions are defined. You'll also see that it's green in the bottom right to indicate that everything's defined. So now we have to save it before we run. We can just call this one draining. Now it's all set to run. Okay, so here we can see that design alerts were triggered for both pipes at different times where it violated the minimum pressure. We can also go over to the graph and view this using a profile plot. And we'll leave it as a single path through pipes 1 and 2. We can animate this using the output. And so we have static pressure already here, and then let's go ahead. We can add another parameter, and we can do the filling and draining gas volume percent. And then let's check this design alert box and hit generate. And we can adjust the speed here and play and see what it does, but we can already see the maximum and minimum pressure here and the steady state gas volume percent here. This one is an air valve. We didn't put any pockets there. You can see it's all 0 initially. So on the bottom, you can see the pipe draining. It doesn't drain all the way. In this case, we would probably want to lengthen the simulation if we were doing analysis, but in any case, you can see above that it's dropping below this design alert for the -10 PSIG. So this is failing our system requirements. We can go ahead and save this graph to reuse. I'll just call it profile plot. Okay. So this one will be our 1-inch squared scenario. And we can right click on base scenario, create child, make an 8-inch squared scenario. And we'll just adjust both of these to 8. And run that again. We're not seeing any design alert messages. We can check the behavior in the graph results. And this time we can just load the plot that we made last time and it'll be updated with the new data. Yeah, we can play that one. And you can see that now it is draining all the way. So it's draining more quickly. That's one thing to notice. And then we see that it's no longer violating the pressure minimum. So this is passing the design requirements. So this is a multi-scenario profile plot of the minimum and maximum pressure profiles. Maximum pressure is before the air valve opens, so it's identical for both scenarios. But the pressure drop across is too great to maintain the minimum pressure during the siphon event. This is possibly due to sonic choking, but not necessarily. It could just be insufficient gas flow. So the incoming air was able to displace the leak when using the 8-inch square air valve. And this reduces the risk of the pipeline crushing during an emergency. So this next example is for system filling on startup for a firewater system. So this is meant to model the filling of a system that's initially dry. And it might be helpful to grab a screenshot of the dimensions on the right before we switch back to impulse. I'll give you a moment to do that. This time we'll be modeling the water in the air at 80 degrees. We'll still just stick to using air. And we'll assume that the system is dry downstream of the pump, but we'll start the pump wet so it can add pressure. All right, so go ahead and open a new model. Okay, we'll start with analysis setup. We are using water again under impulse standard. But this time I will set that to 60 degrees. And then here in the transient control group, let's open the transient cavitation panel. And again, we'll switch this to enable pipe filling and draining. And we'll leave these as default. Okay, so let's start building the system. I'll start with an assigned pressure boundary at the inlet from the main. Actually, let me change the drawing mode and show the grid. So right now it's in 2D freeform. Let's go ahead and make this isometric. And we'll move this down here. I'll bring up pump over the first branch. The second branch right above that. Another branch over here down and to the right. And another branch in this direction. Now I'll start bringing in our spray discharge junctions. One here. One here. And 3 in the other group. And I'll double click on the pipe tool and start connecting these. Starting with the origin. All right, so those are all set. And what I can do to give all of these the same elevation up here is just drag highlight them like this. And under this global edit, you do global junction edit and common data. Put in the elevation. These will all be at 50 feet. They're already selected here since we've selected them on the workspace. And then check the box next to 50 feet. And then hit apply and OK. And we can do the same thing here. Set these to 0 feet. So elevations are defined. And then I will shift click these 3 pipes. We'll do ANSI steel again. We'll do 4 inches. This time I'm not setting the length since I'll do that for them individually. Just a moment. Okay, let me just do everything except length. Okay, let me invert these to choose the other pipes. And all the rest of these should be 3 inches. I'll select everything but length again. Actually, almost all of these will be 10 feet, so let's just specify that too. Okay. This pipe here, this pipe 4 to this system. Let's just change this to 50 feet. Set pipe point here to 20 feet. Pipe 2 to 10 feet. Pipe 3 will be 50 feet. All right. This pipe one will be liquid full. Let's set the gas properties in pipe 2. Do this filling and draining tab. We'll do a 50-50 interface. We want it to be wet on the pump side. And let's specify the pressure here and PSI gauge. And that's 0. We'll do a user specified temperature of 80. So for these other pipes that are starting dry, we can do a box select from the right to the left. I'll just do these ones through the global pipe edit. We'll make them all gas full. We could also use the ambient pressure option here. And set this one to 80. So we'll go down to the filling and draining section. We'll just click this to select them all. And let's apply those. Okay. Now for the assigned pressure junction, let's just set this one to 50 PSIA. The pump, we'll do the centrifugal pump option with the standard curve and set the rated pump speed to 1500 RPM. Click here to enter the curve data. For the volumetric flow rates, we'll leave this in gallons per minute. Do 0, 1500, 3000. We want this to be in terms of pressure rather than head in PSI. So let's do 400 PSI, 450, 350. We'll leave this as second order. Generate a curve fit now. And I hit OK. And the spray discharge, we can just do global junction edit. Spray discharge, select all. The loss model for the liquid side, we'll do a discharge coefficient. And we'll actually do the same discharge coefficient for both sides. We'll leave this as spray nozzle, so 1 hole each. Here we want this to be a 0 PSI gauge for the atmosphere, and we can set this to 0.8 and 0.5. We want this in square inches. Okay, that all looks good. So for the optional, we need to click the gas vent properties. Here, we're defining the combined CDA, not CD and the area separately, but it's 0.4 inches squared, and then this is 80 degrees at the outlet. Hit OK. And we can go ahead and just apply all. So all be exactly the same here. Oh, I changed the elevation to 0 feet by doing that. Okay, make sure that stays at 50. Okay. Um, Okay, so the simulation duration is still undefined. We can define that as 2 seconds. And then we want to adjust the sectioning again. So we can go to pipe sectioning and output and sectioning, and we'll switch this to a fixed count of 20 sections in the shortest pipe. And hit OK. And we'll save this. Just save it as filling. And it's ready to run. I'll just hit OK with the water hammer assistant. It's just letting us know that there's no transient data input. We don't need to define a transient event since it's the filling that we want to define. So those resolution blocks I mentioned earlier, you can see that in this case, it took 157 and they were limited to 500. So if it took more than 500, we would have to raise that limit. In some cases, it might also be worth tightening these tolerances. So the default tolerances are in terms of absolute pressure or relative pressure. So it only met the absolute pressure, but you can set it to meet either one that you'd like, or both, or in this case, either. And the simulation time is heavily impacted by sectioning. So these are going to tend to have longer run times than your typical liquid full impulse models. Okay, so we're seeing a warning here about the transient static pressure at pipe 1 being negative. So that's going into the pump. And the reason it's negative instead of the vapor pressure is because the cavitation modeling is mutually exclusive with the filling and draining. We also have a caution because we didn't use a 4-quadrant pump curve, but for this model, it should be okay. And we can go to the graphs. Actually, first, let's do an animation. If you go back to the workspace, down here where it says workspace layers, we can make a new layer and then click color map and animation. We'll call it filling. Click the gear to open the settings. The color map is going to be for the steady state, so we want this one to be an animation. And for the parameter, you want it to be the filling and draining gas volume percent. So you'll see the gas regions here in red, the liquid in blue. And we can adjust the speed on that to about 80%. Hit play. And there you can see the system filling. It fills in these branches first. And if we were doing a pressure animation, we would see that the pressure waves are reflecting in this area first before they're reflecting from this area. Going back to the graphs, let's do a graph of the pump. So we'll click transient junction. And our pump is J2, so click J2 in this arrow. And we'll want to graph a few parameters. Let's do the inlet pressure. We can just use the stagnation pressure. Add another parameter. We'll do the pump power. Oh. and the volumetric flow rate at the inlet. Okay. And you can see here where those negative pressures happened. We were starting this at 100% pump speed. So if we were doing a more realistic startup or using a throttling valve, we would see less of that. But in this case, it would definitely be cavitating at the beginning. Again, we're not modeling the actual cavitation. We're just seeing that the pressures are below the vapor pressure, and in this case, actually below zero. Now let me just go over the rest of the graph here. So you can see that the volumetric flow is decreasing as the system is filling, which makes sense. The power is decreasing with the volumetric flow. And you can also see in the pressure results up here uh, that water hammer is visible. And again, that starts at the upper branch. We can also see there that cavitation would be present. Since we're using pipe filling and draining, we're not modeling the cavitation, but we can see that it would fall below the vapor pressure. In this case, since the filling is more important, that's a worthy trade-off. But there may be systems where the cavitation is a more significant driver of water hammer. And in those cases, you may need to try to break up your system into two parts and do part of it with filling and draining and part of it with cavitation, or decide which is more accurate. If it's a complex system where that wouldn't be feasible. We can also see in all three of these graphs that shortly after it finishes filling completely, the system stabilizes as we expect. So our overall key takeaways from this webinar, pipe filling and draining replaces transient cavitation models, and it uses discrete modeling approaches for the gas and the liquid portions. This is useful for a wide variety of fields, but especially for system commissioning and shutdown or modeling system failures. This feature can be used to model how gas bubbles interact with pressure surges and forces in the system. And it interacts with other features you're familiar with, an impulse to visualize system behavior, to flag problems, and to ease comparisons between your scenarios. But be mindful of your assumptions and limitations to ensure that you're using the optimal modeling approach and that those assumptions are acceptable for your system. If you want more information, our website has a variety of resources. You can watch previous webinars to show you other features, modeling techniques, or applications that are specific to your industry. We can also put you in touch with a sales engineer who can show you our software and get you a trial license if desired. For existing customers, our support team is also available to address your questions and provide model troubleshooting, and we are always happy to help. All right, well, here's our contact information, and thank you all again for joining.